Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program. Local broadcast is made possible in part by Pfizer.
I suppose the main message I want you to leave with is that physics has limitations. I think we'll be able to discuss some of the nitty-gritty of what makes sound and in fact, glimpse very briefly into what makes sound good, what kind of sound good. But after that, it's really a matter of taste and culture and so forth. And physics only goes so far to describe those. But I think in underlying the fundamentals of these questions, we can maybe have a deeper appreciation of the more complicated, the psychological aspects of music and music appreciation. Up here is the reading in time. So what's going to happen is a cursor is going to move through this thing in time, and that's about 40 seconds. I think this whole piece is about 4 minutes long, so I can show you the whole thing. There are two of these signals because this is going to be broadcast in stereo. So there are two separate channels. Just concentrate on one of these. It really doesn't matter which one. Does anybody recognize this piece? All right, well, there's a lot to look at here. You see lots of time scales. First, the piece is 4 minutes long, but boy, look what's happening here. We have, by the way, I didn't tell you what the vertical axis means. This is, if you want, it's volume. When things are loud, there's going to be lots of wiggles up and down. Here, it's pretty soft. Here, it's really soft. Okay? Now, it's 4 minutes long, and it seems actually pretty simple, but when you dig down deep, you can expand this more and more. We see all different time scales emerging. So here's a time scale of about, let's see, 15 to 20, about 10 seconds. That lasts 10 seconds, that's 10 seconds, that's 10 seconds. That's a phrase, and those of you that play any musical instruments, you know after about 10 seconds, you might move on to a different melody or something like that, and that's what's happening here. Well, there's another time scale. Look here, we have this is about 1 second. We see four somethings going on, spaced by 1 second. There's another time interval. But I would say the more interesting time interval is looking way deep down. We're zooming in. All right, now look at this. I'm really zooming in now. And let me expand this. Here's music. This is, let's see what the time is here. This is 5.63 seconds, 5.635 seconds. So this is 5 thousandths of a second. So this is about 1 thousandth of a second, a millisecond. And you can pretty much see this is it. There's not anything really happening much faster than this. In fact, there's a lot of stuff happening at about the millisecond time span, though. So things vibrating 1,000 times per second. And we're going to be talking a lot about that today. But let's expand it more and see what happens. Well, it gets pretty boring now. Now you can see these discrete points. What's the time scale now? I think each point here is about 20 millionths of a second apart. And this is a digital rendition of the music that I showed you here. And when your CD player plays music, it's basically playing each of these discrete points at about 50,000 times per second. Now, again, the vertical axis is, in a sense, it's some kind of loudness, but what does that really mean? Well, we're going to talk about that too today. It's the disturbance of your speaker. Your speaker has a diaphragm that moves back and forth. It wiggles. And it's tricky how it gets into your ear, but your ear also wiggles. Your eardrum wiggles, and it transmits the signal to your brain. The signal that's transmitted is it's a rendition of this. So we need to look in this and understand it. Okay. Now, the sheer amount of information in this 4 minutes is astounding. Beethoven's Ninth Symphony is an hour long. And like I said, if your CD player is sampling 50,000 times a second, that's a lot of information. In fact, each one of these waves in time can take lots of different values. You can see there's this one's higher than that one, that's lower than that one. So you have to split this up. There's a lot of numbers here. In fact, modern CD players describe each point here, each dot here, by a 5-digit number, up to about 60,000, from 1 to 60,000. And that's coming across your speakers at an alarming rate. So Beethoven's Ninth Symphony being 1 hour, if you do the math, it turns out that's about a billion bytes per second. Sorry, a billion bytes total. It's a huge amount of information. And whoever wrote this music, you have to wonder, how did they find the time to write down a billion pieces of information? Well, that's one of the things I want to point as well. This is a physicist's view of this music, but a musician's view is quite different, and we're going to talk a little bit about that too. If things are happening as fast as 1/1000th of a second, sorry for all the numbers, so 1/1000th of a second, 0.001 seconds, and the speed of sound is about 350 meters per second, then you can think of this sound wave as actually traveling from the speaker to your ear, or from an instrument to your ear, and that time scale of 1/1000th of a second actually has a length scale because it's moving to you, and that length scale is just the product of these two. So something that's moving this fast for this amount of time, it covers, it's pretty even, I can do that, 0.35 meters, about this long. So the standard length scale in what we hear, what we talk about music, is about this big, which is good because that's about the size of our head. That's about the size of instruments. That's about the size of this clarinet, which we'll show later it makes music. It's about the size of piano strings. Lower instruments will be bigger and so forth, but I just wanted you to see that length scale as well. You may have gathered by looking at this is music of mass destruction. In fact, literally, it's music of mass destruction. This is the Dies Irae from Verdi's Requiem. Now, Dies Irae, you know in Latin, is the day of wrath. It's the judgment day, and it's terrifying music. So let's dive right in. Okay, I've read that this is the loudest music, unamplified sound produced by man. At least this was true in the late 19th century when Verdi wrote this. So the Requiem Mass, as you know, is a mass for the dead, and this really is music of mass destruction because on Judgment Day, the Lord comes down and people are to be judged. Now, you look at these waveforms, they're very peaky. They move around a lot. They seem kind of random, especially when you look at these big drum beats. And I want to contrast that with another section of this piece in a minute. So lots of wiggles, lots of information here. It's very complicated. You can see lots of different time scales here. Now, a little later on, the next part of the Requiem is the tuba mirum, which is the literally, I believe the translation has to do with trumpets blaring. The trumpets are collecting all the people to be judged. And now the trumpet sound is a nice sound by itself. It's a much simpler sound than we had here. And you can really see a qualitative difference in what these waves look like. Look how smooth they are. Much more regular than the other stuff. And the music sounds much more regular. Now all hell breaks loose. Literally. Again, this is supposed to be terrifying. Okay, I'll leave it there. Okay, enough of the Requiem. We have to move on to lighter things. So the question is, did Verdi write it this way? Of course not. He would have had to write down a billion pieces, a billion numbers down, a billion bits down. And that's not, of course, how we read music or write down music. This is an excerpt from the score. Actually, it's reduced for chorus and piano. In fact, this is probably a half a minute of music, very much simpler than what I presented here. I guess there are 2 points I want to talk about then. I want to make a connection between these two. In fact, why can we make such a simplification from this very complicated sound wave, if you will, and this very much simpler set of notes? I put this one up because I really want you to not think about mass destruction anymore and think about a little more light music. So this is a piece near and dear to my heart. So I'll play this real quick. Just again, the main point here is just to change the mood. So it's much simpler. Much simpler. That was a half minute of music, and you'll note there was much less information on that score than in the sound wave. So the big questions are, why are there only, many of you know, there are only 12 notes on the piano. There are 12 unique notes. Here's middle C, see on the camera there, and there's a C up above, an octave above. And there are 12 unique notes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then it repeats. Only 12 notes. That's pretty easy. The question is, why only 12 notes? And we're going to, later on, I'll try to convince you why. And it comes down to numbers. That's kind of cool. Also, it comes down to culture. Music with different numbers of notes sounds a little odd to us. And we'll have some examples of that, too. Another thing, in the Verdi score, there were many different instruments playing, although that was a piano reduction. Strings, violins, woodwinds, percussion instruments, the chorus, 4 voices of chorus. These instruments sound different. And Verdi wrote the music for these instruments because he wanted them to sound a certain way. Why did the instruments sound different? So we're going to talk about that as well. In the end, though, this is, if I go back to the computer here, in the end, this is all there is. It doesn't matter how you represent the music. That's all there is to it. But nobody looks at music like that. I mean, you could not recognize what this piece was by looking at that waveform. Okay? But we're going to talk about this, the physics of this waveform, and the different time scales and so forth, and relate it to these notes we have over there. The 2 topics I want to talk about, the first one is, what is sound? And the second one is, what sounds sound good? That's very important. If Verdi didn't make music that sounded good, we would not have heard of his name or anybody else that wrote music. So what makes music sound good to our ears? And they're both rooted in math and physics, and that's fortunately what we'll be able to talk about today. Okay, so let's talk about the first one, the first topic here. What is sound? And this is really hardcore physics. What is sound? Sound is a wave, if that means anything to you. Now, a wave is, you might think of a wave as just an oscillation. It's not quite that. But we did see all these oscillations in the music, so somehow an oscillation has to be in there. Well, a slinky is an oscillator, of course. This is a very common oscillator. It goes up and down. Of course, this is much slower than that one, about 1,000 times slower. But oscillations are a very important part of sound. Now, oscillation by itself is kind of boring because somehow we have to talk about a sound wave or energy going from my voice or the instrument to your ears. And so it turns out that in general, waves come about when you have a spring like this, and you also have a medium where the spring can be transferred to another spring and so forth. And a good example of that are these pendulums, these big pinballs, all coupled by little springs. This is a big giant oscillator. But you have to imagine that while we only have we have 8 balls right here, you could imagine having 8 million of them connected by springs. And it's not simply going to oscillate. You're going to see something moving. Watch when I just disturb one of them. You kind of see it. You see it going over here, then it reflects and it comes back. So something's moving. And that's in fact, that type of an oscillation is very much like a sound wave. And when you look at each individual ball, it's not really moving anywhere. This ball is staying here. It's not going over there, but something is going through and back. Another example is this so-called Jacob's ladder. You may have seen these things. This is a torsional system, and I can set up a wave just by doing that. You can see none of these wooden bars is actually moving up, but something is moving up and coming back down. And a wave always concerns itself with something that's oscillating and some kind of spring. And in this case, the spring is the torsion right here. It kind of feels like a wind-up spring. A nice animation on the computer of actually what a sound wave is. Air is what transmits sound, and this is actually a nice model of air. All right, well, it's not so great. We only have 8 air atoms here, air molecules. But they do collide. Air molecules collide with each other, and there's an effective spring. And we know what those values are, and we can calculate how fast this thing moves back and forth. Now, I want to write down a very general, this is the only line of math, and you'll see right away, outside of a square root, there's a lot of English words in this math. The speed of a wave is generally equal to the square root of something, and that's the only hard math. Here, it's the square root of springiness. This is the technical term, anyway. And weight in the denominator. Don't worry about the square root. It's not important. The important point is, if you have a more springy thing, the speed of the wave is going to be a lot faster. If the thing is massive, the speed is going to be slower. We're pretty familiar with that one there. I guess these days you'd call that you wouldn't call it an equation, you'd call it a math sentence, right? Okay. So this is important. There's a lot of physics here. It tells us how a lot of musical instruments work, actually. So what about air? Actually, we know air is pretty light. The little molecules that make up air are very light. In fact, there's a lot of them packed together, so they're very springy. So you'd expect that the speed of sound in air is going to be quite fast. I like this animation. Each one of those dots is supposed to be an air molecule, nitrogen molecule, I guess. And there's a piston over here driving it. You can think of that as a clarinet or something, some instrument. It's producing something. Now, you can clearly see something going from left to right. In fact, you can even see something going from right to left, kind of the reflection. But pay attention to an individual dot. Pick one out. Is it going anywhere? No. So waves are very interesting. It's not that stuff is moving. It's that energy is moving. Okay? Another good example is this rope right here, which I'm going to have to untie. This is one of my favorite demos. Sorry. I'm going to trip Okay, so we can excite waves on this rope. In fact, they can go from me to the wall. And in fact, they'll reflect. They'll come right back. And so I'm going to hold the rope rather loose, and I'm going to give it a pluck. You see it go over there and come back? I'm going to hold it looser. Slower, right? I'm going to hold it really tight. Really fast. Okay, so that's the numerator. I'm making it more springy. By putting it under more tension, it's more springy. Of course, I'm not changing the weight of this rope. That's always the same. But I can change the speed of the wave going through this rope simply by applying a different force. Well, this is basically a piano string. It's held at both ends, and you strike it with a hammer, and you get waves. To really make a connection between music and these waves, there's a nice demonstration here set up. You may have seen it. A bit of turn on the gas, though, and it makes a connection between a musical waveform and something you can visualize. It's a lot like the rope, but this is actually really real music playing. And what's happening here is there's a loudspeaker at the one end and this big metal tube that's closed at the other end. And we're going to send sound waves through here. And if you've ever cooked, and I know everybody's cooked on a flame, if you have a current above that flame or some air current or a fan on, the flame moves around. Well, we're going to be moving around the air underneath here. And in fact, it's going to change the flame pattern. And the flames that you'll see will be reflected by the sound wave underneath. So what I have here is a simple waveform generator. It moves the speaker back and forth very smoothly. And we should see the pattern. Now that's a lot better. We should see the pattern in these flames. And certain frequencies of the sound will result in much bigger changes in the flames. There's one right there. So you can, this is kind of a musical instrument. It's hard on the ears. These monotones are very hard on the ears. But you can kind of see a direct connection between the sound wave. As I said, it's about this long. Now we're going to actually play some music on that thing. I'm going to feed a very complicated waveform into that flamethrower. No, it's not a flamethrower. It's a the flames are going to be very safe, and they're only going to go up, down like that, I think. But, okay, this is Switched on Bach, which is an old CD of one of the early electronic renditions of Bach from the 60s by Wendy Carlos, the performer here, on an old Moog instrument. And the Bach is particularly good because the notes are very crisp and you can really see the patterns here. So. Okay. That's a nice visual demonstration of a direct connection between the wave that we believe is there and actually seeing it. Okay, boy, we have lots of instruments to go through, so let's go ahead and do that. Now, I wrote down before I erased it that the speed of sound was about 350 meters per second. We can actually measure that because we have a meter stick here. Emily's nicely set this up. We have two microphones. I'm going to make a sound here, and we're going to see the sound wave hit one microphone and then the other microphone. There's going to be a delay between the two. There's an oscilloscope trace here showing the sound wave on this microphone and then the one on the other microphone. There, that was good enough. I'll do it again. You see two sound waves and they're delayed in time. Now an oscilloscope measures signals, and again, like the one I showed before, time is going to the right. And this, the top trace was this microphone, and the bottom trace was this. And I better not speak too loudly or it'll trigger again. Now you can't really see here, but, and so that's, I don't know, that's about 3 boxes. Let's say 3 boxes. Yeah, for the heck of it. I have no idea what the speed of sound is. I mean, okay, so that's about 3 boxes. 3 boxes, and each box is 1 millisecond. So the delay was 3 milliseconds. Sorry if you can't read that. I'm just writing 0.003 seconds. And I know, in fact, since this calibrated meter stick is just about perfect, that the separation was 1 meter. So I can therefore calculate the velocity. 1 meter divided by 0.003 seconds. Look at that. It's exactly 333 meters per second. OK, so speed of sound is very easy to see. And you all know about the speed of sound when you hear echoes and there's certain delays. And the time scale is, again, about a millisecond. OK? A millisecond's a foot, remember? This meter stuff. 333 meters per second, that's about 800 miles an hour if you want to use real units. I spent a good part of my career at the National Bureau of Standards, and it was funny, one of the older guys there in the atomic clock world, he told me, this metric system, it's a fad and it'll pass. so I mean, this doesn't mean a lot to you, but 800 miles an hour, you know about that. That's faster than you go on a jet, for instance. Okay. So we have a little bit of an appreciation of sound waves. Now, I want to write something down next to this 333 meters per second. Anybody know what the speed of light is? Light's a wave. Well, light is 300 million meters per second in metric. All right, 300 million meters per second. So what do we know about light then? Well, light must be whatever it's traveling in, it must be very, very springy, and it must not weigh very much. In fact, light weighs nearly nothing. In fact, it is nothing. It's tricky. Light's tricky. That's another subject altogether. But whatever light travels in, if we go back in time 150 years, this was a problem. People were trying to make sense of light waves because this is what we thought every wave should do. And light was a problem. It seemed to be infinitely springy. Okay? Interesting. Okay, so waves are everywhere. Now, I want to go back to this. Now this software, it's called SoundForge, and it's nicely on loan from the demo lab here. It analyzes any sound file you want to put into it, but in addition to this type of a wave, it also allows you to do something called the technical term is a Fourier transform. But what it does is it tells you what notes are present up there. And maybe we should find something a little, well, actually, we will do the Verdi, but the nice part, the trumpet part. Now, a little description down here. On the bottom, as this music is being played, you see these peaks. These blue peaks are appearing. They're discrete. Those are notes. These are the trumpets playing and the overtones that come from the trumpets, and it's a nice spacing. And this is a little more what Verdi had in mind. He wanted to see that. He didn't really care about the upper trace, okay? You can see the three of them down there. Do you see three peaks? Three trumpets playing right now. So now we're moving on to this next topic. What sounds sound good? I can't just put any random peaks here, any random notes together. They don't sound great. And so we're going to talk about that and do some demonstrations with well-known instruments. We all know on the piano what notes sound good and what notes sound bad together. That note by itself sounds good because there's nothing really to compare it with. A C. A C always sounds good with another C. All these octaves, they're all the same note, really. In fact, the reason they sound good together is that these notes have an intimate relationship. And I'll talk about that in a bit. The perfect fifth, a C and a G, that sounds good too. Any fifth sounds good together. But if you actually, I don't know if you can see what I'm doing here. I'm playing a C and a G. If I just take that G and move it a little bit to the left to F sharp, that doesn't sound so good. Okay? And the reason it doesn't sound so good, there's math behind it. It's actually pretty simple, and we're going to talk about that. Now, there are two levels of what sounds good and what doesn't sound good. Now, when I play an individual note, in fact, that note's very complex. It's not a simple tone. This oscillator is a simple tone. Is it off? No, we got another one here, right? That really bothers me. It's a tone that nobody would make an instrument based on. The instruments that sound good produce tones that have many different notes on them. And in fact, we saw that on this waveform here. When the trumpets were playing, even the single trumpet at the beginning here, That's one trumpet. Look at all the notes that's coming out of it. Now, here's the math. If you look at these notes, what are they? Well, in fact, I can move the cursor and find that out. This one's at about 300 hertz. That's an E, I believe. 300 hertz, 600 hertz, 900 hertz. See a pattern? 1200 hertz. They're all multiples of something. Those are overtones. And instruments that produce overtones that are simple multiples of each other they sound good together. And in fact, remember all the time scales that are in music. Think of rhythms that sound good together. And I'm going to play a drum here a little bit. You can have rhythms beating against each other, and some of them just sound awful, and some of them sound okay. Like this I'll play one drumstick on the rim, another one on the drum. But that sounds good together. It has a beat. It's 2 to 1. One's going twice as fast as another, all right? Or 4 to 1's good. But you can have all kinds of ratios that actually sound okay. You could dance to these. 3 on 2. That sounds all right. It kind of repeats itself in short order. Even 4 on 3. A little bit more complicated, but it still repeats. So it's these ratios, fractions, have a lot to do with what makes music sound good. 2 to 1. We want simple ratios that repeat each other. And not only for a beat, but also at the millisecond time scale. We want notes together that have relationships. Now, this C and F sharp I played is an interesting one, and it sounds bad because that ratio is not it's not a good fraction. It's not a fraction at all. In fact, theoretically, that ratio should be the square root of 2 to 1. The square root of 2 to 1. The square root of 2 is what we call an irrational number. If you write it in decimal form, it never ends. Therefore, you can't write it as a fraction. Okay? So I want to go through a bunch of instruments now and start to talk about what modes these instruments produce. And of course, all the instruments are going to sound good by definition. Let's start with the snare drum. This one doesn't sound good. What note is this? That's not a note at all. It's a sound. In fact, I have this piece of software even records music, so I'm going to set it on record. And play a little drum roll. A little loud there. And there's the waveform. And I can play it back for you. I could hear my daughter there screaming in the middle. Okay, so let's analyze this signal here. Trim, there we go. Did you look down below? Nothing. Boy, look at all that stuff. There are no peaks, no ratios or anything. Of course, that's what a drum does. It produces modes that aren't related to each other. In fact, numbers like the square root of 2 are in all the modes produced here. And that's why a drum really doesn't have much pitch to it. To make a drum have pitch to it, you have to shape the bowl in a very special way. And it's very difficult to do that. So we have a few instruments here. Why don't we start with actually, Mary, would you like to, my daughter Mary Monroe would play the piano. She'll just play a few notes for me, and we're going to record what a piano note sounds like, and look at those tones. Good. Let's see what we got there. Yeah, we got something. Look at those beautiful harmonics. They're all over the place, and they're all related to each other. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You can see 15 harmonics. So the waveform in time, if you look at it, you can, even though it's a complicated waveform up there, it repeats itself. And so it's pleasing to our ears. Okay, what's the next instrument? How about a flute? Now, a flute's a very special instrument. Before you start playing that, a flute, it's much more complicated than a string instrument. A flute is basically a tube. And it turns out that when you produce a sound on a flute, I can kind of draw the wave in space. Looks like this, and it oscillates back and forth. This goes up and down on either side. And the important point is, on either side, there's an open-ended part of the wave. And in the middle, there may be what's called a node, where there's no disturbance. And this is one tone that's played on a flute. But you can play any tone on a flute at a given fingering as long as it's open on both ends. So there's one wave if you want, one frequency. Another one is this. Remember, it has to be open on both ends. Another one is this. So you can put all those notes together, and we're going to measure just that. Ready? How about a lower one? Good. Thank you. Let's look at that lower one. Okay. Again, the waveform up here, I mean, it might look, well, actually, it's different than the piano, way different than the piano. And now let's look at what it looks like downstairs. Okay. Unlike a piano, it only has a few tones in it. But you can see they're related in a very simple way. This is at about 460, 950. That's twice. That's 3 times, 4 times. So there are a few of these harmonics, and that's characteristic of a flute. And you can pretty much see that from this. It's a little hard to see that, but the lowest frequency one corresponds to this really thick guy here that I'm drawing. And the next one is twice as fast. It's this one here. And 3 times and 4 times. I guess we're okay. We got to move through the instruments. So thanks, Natalie. The next instrument you might think it's the same thing. It's a clarinet. And the clarinet, in fact, it's just about as long. So everybody knows a clarinet and a flute are the same thing, right? So let's. Whatever note you want. Yeah, lowest note's good. Good. That was the good part. This is fun. Let's just look at the waveform. What does it look like? Different than the flute, for sure, and the piano. Okay, look at these guys now. Now this is where it gets fun. First, I should say that these units, each division here is a factor of 10 in loudness. So actually you can forget about this one. It's 100 times softer. So really we want to talk about this one, and this one. Well, this one here is at about 200. This one's at about 600. It's 3 times. So we're pretty much missing the second guy. That's the difference between a clarinet and a flute. And the physics of that has to do simply with the geometry of a clarinet versus a flute. A clarinet looks just like a flute, except one end is pretty much closed, and that's because it's a reed. It's closed at one end, open at the other end. A flute has a monster hole, even at the mouthpiece end. So we call it open on both ends. So clarinet is closed, so the sound wave that's going in there the air can't move here. So the first sound wave is going to look something like this. Okay? It's open at the other end, so you have this type of a maximum in the wave, and here you have a minimum. Well, what's the next note, the next type of a tone it can support? It looks like this. And it wasn't clear from my drawing, but that's actually 3 times faster. The next one is 5 times faster. 7 times, 9 times. So it has only the odd harmonics. And you can see that clearly from this. So a clarinet has a different sound than a flute, has a different sound than a piano. I wish I had time to show a violin. A violin, you can see 20, 30 overtones, just like a piano. So this gives you the different, what's called timbre, T-I-M-B-R-E, of the various instruments. Now, there's a fun demo over here that shows how instruments can vibrate in such a way to produce these modes. And in fact, the fingering of the woodwind instruments will allow you to show that. And then we're going to move on to 2 more instruments really quickly that depart from what we showed. So this is the wine glass. Everybody knows how to make a wine glass sing. So we have a camera up here on this wine glass. Maybe hear that note. I'm going to put these on because this is kind of a loud sound toward the end there. But so I've got we've got a speaker that's driving the wine glass, and the wine glass is vibrating. We have a strobe light also. This is at about 500 hertz, 500 cycles per second. You can't see it, it's too fast. So we have a strobe light here near 500 hertz. So through the magic of strobe lights, it slows it down so you can see a little bit of a beat note. And as I tune over it, you can really see it move. I'm going to turn the volume up a little bit. So can you see that? Can you see the whole wine glass is oscillating in a very funny mode? And in fact, so wine glass is an instrument. It supports modes like that, and those vibrations get transmitted to the air directly, and we can hear it. What you're hearing is the speaker now, not the wine glass. But unlike most instruments that are not made out of glass, this kind of instrument can break if you play it too loudly. Didn't break. Let's try it again. All right. Take a bow, please. If you know what a glass harmonica is, it's an instrument that actually Mozart used, and it was invented in his day, a bunch of spinning glasses with lots of water, and he wrote music for the glass harmonica, and it sounds just like this note you know of when you play a wine glass like this. And these have been pre-tuned to a nice scale, so we can. That one's a little off. All right, ready. Hold on. There we go. All right. We don't have time to record all the spectrum of those, but there are two more instruments that are kind of puzzling. And the next one is the saxophone, which is much like the clarinet. It's got a reed, closed and open-ended, so you would think that it would sound just like a clarinet. My daughter Kate Monroe will demonstrate the saxophone for us. We'll make a recording and do the same exercise. Remember, the clarinet showed these odd overtones. Good. Okay, there's the waveform. You can jam if you want while I'm doing this. All right, let's expand this. Take a look at the waves, whatever that means. All right, I don't get much out of that, but it's interesting to see. Okay, it looks more square-like, doesn't it? Well, let's look at the spectrum. Well, what happened here? We have the lowest note here, which is about 220. The next one is, well, wait a minute. The next one is at 440. It's not like the clarinet. Remember, the clarinet only had odd overtones. This one has all of them, kind of like a piano. So what's the difference? Does anybody know? There's a hint. There's a bassoon, and Mark Acton will. The bassoon is so cool that I figured we really had to get that sound recorded as well. What's different about the bassoon and the saxophone versus the clarinet? Just look at them. Can anybody notice the difference? Straighten out the saxophone, all right? You can bend that. It doesn't matter that this curls up. It's longer, but that's not going to change the pattern. That's just going to change the note that you play. Yeah, I heard the word was tapered. You see that clarinet has the same diameter up top as it does down at the bottom. Of course, down in the last it bells out, but don't worry about that. If you remove this, the clarinet actually sounds pretty much the same. But a saxophone is conical. It starts out at a very small diameter, and it grows to a very big one. And look at the bassoon over there. Near the mouthpiece, it's tiny, right here. And it just gets bigger and bigger. Of course, it wraps around itself. It gets big, and by the time it's out here, it's huge. And so a bassoon and a saxophone are actually, I would say, more closely related than a saxophone to a clarinet. All right, let's get a bassoon sound. Bassoon is a notoriously difficult instrument to play. Nice. Oh yeah, let's hear the. Good. So again, like the saxophone, you end up having, it's a little hard to see here, that's 200, 300, 200, 100, so that's about 180. And we're missing one down here, but they're spaced by every multiple of some fundamental. And the reason is it's the conical shape, and it's really complicated actually. You can't make arguments like I did here. As soon as this thing is conical, then the wave, it kind of wiggles fast here and then it goes slow. It's hard to draw it. I don't even know how to do it. I don't quite understand that. Now for the last instrument, for the last instrument we have Emma Mickelson will play a French horn for us, which is, sorry, Emma played the clarinet. Her twin sister Rachel, that's why I'm getting confused. Rachel will play the French horn. Now brass instruments, there's no simple theory. Turns out they're the most complicated. The physics of brass instruments is so complicated, it took hundreds of years for them to evolve to their current stage. And it has to do with, I mean, number one, you can see that it starts out pretty small and it kind of gets wider. But there are these valves that allow the air to go through different passages. And the exact shape of these valves is really difficult, how many bends you have. And they had to take hammers and make these things just right throughout the years to have what we have today. Good. Actually, I like this one. Let's see the middle section there. Sounds like an elephant or something. I'm trying to stop it right in the middle of it. Well, anyway, it is very complicated, actually. The brass instruments, they don't have nearly as many harmonics as strings or other woodwinds. And the trumpet and the trombone are just as complicated. Make an elephant sound. This is, I love this stuff. Go ahead. Good. All right. Okay, boy, there's a lot of things I want to talk about. One is that I never answered why are there only 12 notes? In fact, the French horn, the clarinet, you can play many more than 12 notes by fingering just right, but a piano is fixed. You can only play those 12 notes. The question is why? It's a deep question. And to maybe get an inkling there, let me play some alternative pieces that have different numbers of notes in their scales. These are going to sound rather strange. This one is I believe it's a 7-note scale. All right. The opposite extreme, there's another fellow by the name of Adrian Fokker, F-O-K-K-E-R, like the German aircraft, who has a keyboard that has 31 notes in the scale. It never really took off. Let's play this one. This is called for 31 Elises. If you know Für Elise on the piano, this is standard here, but listen. I don't know, it never took off. I have no idea why. So we're stuck with our 12 notes. All right, so why 12? All right, so we're just about done here, and I'm going to tell you why 12. And the only math involved is multiplication. If you know how to multiply, then I can tell you why 12. And the rationale is that we like fifths. We like perfect fifths, like a C and a G. So I'm going to start at C and keep going up in fifths. Low, very low C. It hits C again. We went through actually 12 of those. Let me count them up again. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then C again. Well, there's something funny there because I can also go up in octaves, which is a factor of 2. That's 7. 1, 2, 3, 4, 5, 6, 7, then back to the same note. So it took 12 steps of fifths to hit 7 octaves. And what we need to know is that an octave is a factor of 2 in frequency. The note is happening twice as fast. And a fifth is, again, that nice ratio, one of the fundamental ratios, 3 to 2. The faster one is 3, the slower one is 2. So a fifth is 1.5, 3 halves. And the reason we have 12 notes is that it turns out that if you do fifths 12 times, so 1.5, and you keep increasing the frequency 12 times, that's an exponent. So I'm just multiplying 1.5 12 times. That number turns out to be about 129.4, I think. It's about 129. And you'll also recognize that's near a power of 2, because 2 to the 7th is about, well, it's exactly 128, but it's about 129. And so the mathematical reason we have 12 notes is that we can get all the fifths in there and the octaves, the two most important. And it's only an approximation. Okay? And so when you tune a piano, in fact, the octaves are perfect, but the fifths, you actually want this to be a little lower. You make this like 1.49 to the 12th, and then you can make that exactly 128. And then the octaves are perfect, but the fifths are a little flat. That's why we have 12 notes. And it's also a cultural thing. We've been born with 12-note musical systems. The Western civilization is based on the 12-note scale, and that's why it sounds right to us. Now, there are many other cultures that have different scales, in fact, continuous scales. And as the last demo, I'm going to demonstrate an instrument invented by Leon Theremin. There he is, playing the Theremin box. You may have heard of this. It was the first electronic instrument. And it's based on, there's no wind instruments here, it's based on electronics. Inside here, there's a capacitor and inductors and so forth. I'm part of the circuit. I'm going to be a capacitor with this guy. As I move my hand, the pitch changes. As I move this hand, the volume changes. A little too loud, huh? So you can, with control of my hand position, I can play any note. It's hard to play this instrument because you can play any note. So you end up having to have you have to be able to correct your finger position very precisely. And again, I'm part of the circuit, and by varying the circuit, I'm changing the oscillation here. So, and again, this is representative of lots of instruments. And say in India, you hear like the sitar has many different notes, more than 12 notes, and there are other instruments that vary continuously. So since we're really running out of time, this is the last demo. I'll try to play something. It's been a while, but if you want to clap, go ahead. To the beat. Ready?
Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program. Local broadcast is made possible in part by Pfizer.